Welcome everyone, and thank you for joining us today. Today's webinar is presented by Sports Field Management Association. This is the final week of our series of post-conference education. Our featured speaker today is Thompson, Managing Partner for IrriTech Training. Today he will be presenting irrigation system design approaches to minimize surge pressure. Attendees will be muted during the presentation. If you have any questions, please type them into the Q&A feature and they will be answered throughout the presentation. Thank you for joining us today. You may go ahead and get started.
Great. Well, I will echo the welcome. Thanks for taking time out of your busy schedule to join us here today, or remotely, in a recorded version, depending on how you're viewing this. My background in irrigation has been pretty extensive. This is my 42nd year in the landscape and irrigation industry. And as a result of that, I kind of wear two hats. Besides the IrriTech training part of it, I also am actively involved in doing a number of different kinds of evaluations and troubleshooting, as well as water use planning. So we're big believers in training, obviously, and in certifications. As you can see here, it's hard to get a degree in irrigation, so professional certification is the way to go. In the irrigation world, there are a number of independent certifications out there. Probably the most prominent are those from the Irrigation Association. And if you you have my contact information here, and I'll show it again at the end. But if you're interested in industry certifications that might involve the Irrigation Association, I'd be happy to help shepherd your way through there, to clear up any questions or whatever I can do to help you in that regard. So we're going to talk about trying to figure out how we can minimize the effects of pressure surges on an irrigation system, because they're omnipresent, to say the very least. So we'll talk about understanding the very scientific effects of that cause these surges, and then talk about some opportunities to deal with them and to minimize their damage through the different from design to installation to management, that kind of thing. So let's first talk about the hard facts. You're never going to prevent surge pressures. That's just an unfortunate thing. It's like preventing pressure loss. It's going to happen. Every irrigation system happens, and the design, installation, and maintenance and management of the system determine how extensive or how violent, maybe even. Some of you, I'm sure, have experienced some active surge pressure breaks in a system, especially on sports fields, in big complexes and things like that. So again, we can do some really good things to minimize those things. So let's take a look at what causes these surge pressures and what the heck we can do about it. So let's just look at the anatomy of these PVC failures. Now, if you've taken a hydraulics class or a design class, you are drilled completely in the mantra of 5 feet per second is the maximum speed limit. We want the water to flow through the piping system, all the PVC components, and we measure that in velocity. And 5 feet per second is the basics. And the principle is obviously to control the pressure loss. That's probably the key one. We know that as you start to get above 5 feet per second, pressure losses start to exponentially get larger. But as that happens, the velocity is the key physics that causes the surge pressures. So control velocity, you control surge pressures. You'll hear that a million times. Now, luckily, we don't have to do this equation very often, but to understand what velocity is and what the drivers of it, you'll see the Q, which is always represented in hydraulics as flow, is the representative variable for flow in gallons per minute. The ID is the inside diameter. So velocity is directly proportionate or affected by the amount of water we're jamming through the pipe and the size of the inside of the pipe. So the larger the flow in the same size pipe, the bigger the velocity, the greater the velocity. The smaller the pipe size at the same flow, the greater the velocity. So we can make the water go faster by jamming a lot of water through a small pipe. But in fact, we can't generate any pressure. We just make the water go faster, which is where damaging surge pressures come from. So just let's kind of put some perspective behind this moving water stuff in pipe. So if you looked at a cubic foot of water, that's almost 7.5 gallons per cubic foot, and 7.5 gallons of water weighs just a little over 63 pounds. So you have a mass of weight moving in the pipe. And so if you looked at 6-inch class 200 mainline pipe, you're basically going to hold about almost 1.5 gallons per linear foot of 6-inch pipe, almost. Cubic feet are kind of hard to get our heads around. So 1.5 gallons per linear foot, that means every linear foot's going to have about just a little over 12 pounds of water in every foot. So in a 1,000-foot main line, you're going to have a mass of over 12,000 pounds in motion. 12,000 pounds. It's moving, right? And it's moving, well, 5 feet per second, right? So if you had 6,000 feet, now you have almost 75,000 pounds of weight moving. And that's almost as the weight of a fully loaded tractor trailer rig, right? Moving at 5 feet per second. So there is a mass of fairly substantial proportion depending on the diameter of your pipe and the length of your pipe. So just keeping that in perspective, now that mass, since it's moving, the faster we move it, the bigger the surge pressure. So the bigger diameter, the more water, the larger the surge pressure. The longer the pipe, the longer the mass. So imagine a train moving down a track. And if you had a short train that was running down and hit Godzilla there, Godzilla would be like, ow, big deal, right? But with a large, longer mass of the same size cars, Godzilla takes it in the kneecap and gets knocked out. I know that's kind of hokey, but I think you get the rudimentary analogy here. So the longer the pipe or the larger the pipe, the more damaging the surge. That's why residential systems with 1-inch main lines, you don't see, you may hear the water hammer, but you don't get to see the problems quite so dramatically as you would in a larger main line. So surges are created by any change in velocity. And this is the mind-boggling thing about what causes a change in velocity in the water within the piping system. So if you decrease the flow in the same size pipe, then you decrease velocity. If you increase the flow in the same size pipe, you increase velocity. Remembering that the surge happens when these changes happen. So if I increase the inside diameter, in other words, I put it through a bigger pipe with the same flow, it'll go slower at a lower velocity. If I put it through a smaller pipe, the same flow will go at a much higher velocity. That's the relationship, right? So here's the mind-boggling thing that most people don't realize, how this cyclical surge pressure, where it comes from. Obviously, every time a valve opens more powerfully, closes, stops the water, the pump starting and stopping, line breaks, rapid escape of entrapped air inside the pipe coming out of the sprinklers, changes in pipe size, like going from a larger pipe going into a fitting, going out like a T and going into a smaller pipe, or vice versa. Those speeding up and slowing down in velocity causes a surge. And then changes in directions, like T's and L's are the big 90-degree turns, right? So where do the major pinch points go when you put thrust blocks or a joint restraint in? The T's and elbows, because of this surge. So if you think about those components and then you think about a large system, it's got all of those things working all the time in a large system. Looped, even if it's not looped, and you've got lots of zones, a roadway job, a park that just has a single loop and doesn't have sub loops. Golf courses are notorious for all the sub mains that go on in there. So you got multiple increases and decreases in flow. We got different direction changes, multiple valves starting and stopping throughout the process. Just those small changes in flow from one zone to the next. It's not the same huge single event impact like the last zone shutting off when it's the last thing to stop all the flow in the main line, but it's still cyclical in nature. Pipe size reduction is fitting lots of room for entrapped air in a big system. And entrapped air it's usually the thing that causes the big breaks. So let's look at a couple of these things. And of course, we're setting this up to talk about how do we now prevent some of this, the force, or minimize the force. So if you look at this example, if you got water through a 4-inch 90 elbow at 100 PSI operating pressure, if you look at this chart, and this chart is pretty well known, but this one comes out of a document that I'll show you at the end and talk about how if you want to copy designing, operating, maintaining, and piping systems using PVC fittings. It's a study from the late 80s. And you can see that at 4-inch, a 90-degree elbow creates 1,800 pounds of force. That's not pressure, that's force. That's pressure over an area. Pressure times area is force. So that's the old, an object in motion wants to stay in motion, right? It's a big deal. And so in a 4-inch pipe, you got 1,800 pounds of pressure in that little fitting. We're not talking about the 70,000 pounds in the 6-inch main line, but when it comes to that fitting, because in a 4-inch pipe, it's a little bit smaller. You can see further down that chart that the bigger the fitting, the bigger the force. So if you a 6-inch fitting right below that, is going to have the 4,000 pounds, as you can see, if you can see my cursor. So it's a big deal. Obviously, what ends up happening is that surge, when it happens, it resonates in the water column that's in the, if you will, the tube of water that the pipe is. And that just keeps bouncing back and forth and back and forth. And if there's not some dampening feature, like maybe the speed in which it's moving and when it's going one way and it's creating another wave that they interact and kind of dampen each other, it can create a big force. Also, a zone valve, right? When the zone valve shuts off, if you're moving 5 feet per second and 1,000 feet of a 4-inch main line coming into this valve, and the valve closes in half a second, which is pretty typical for globe valves or typical zone valves. If you're a golf course guy, it's more like 1/10 of a second. And you blink in 1/10 of a second. That's how fast the water stops. And I'll show you a graphic here in just a second to talk about this more. So this ends up causing 13,000 pounds of thrust in that pipe. And the surge pressure is about 80 PSI additional to the 100 PSI. So now you've got a 180 PSI surge going in there, and it's moving at 11, almost 1,200 feet per second. It's going very fast. And if you've heard a water hammer where it goes ba-back, 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 that's the sound of the water hammer hitting once, going all the way to the end, then hitting again. And you only hear the one when it's hitting near you, or if you're in the house or the building. So it's a big deal. So that shock wave is moving at 1.68 seconds for every 1,000 feet. So in order to do that, 1,000 feet, that it has to move over 500 miles an hour is how fast that shock wave is moving. That's pretty impactful. So big thrust, big action. So let me just show you this on solenoid closing, because this is going to be one of the key things we can control to help minimize this, the damage from a complete stoppage of water. So if you look at this graphic, you'll see the gallons per minute flow range here, and this is times in seconds. So this whole thing's only 20 seconds long. So you'll see right here where that's the curve of the stoppage of water that I just highlighted. Now, looking at this line, it goes right there at about almost the 3-second mark. So probably what happened is they de-energized the solenoid, and about 3 seconds in, if you monitored the flow would start to diminish, get smaller, go down. But as you can see in here, it's not going down very fast. And it really takes almost, in this example, really probably about the 7 or 8 seconds before it really starts to shut. So we don't measure valve closure time in the time it takes for you to de-energize the solenoid at the controller until the water stops. It happens when the first diminished flow is recorded until it goes to 0. So if you want to have a relative an association, an analogy, well, it's not even an analogy, you want an association with this is, if you're standing next to the valve and it starts to turn off, it's the sound that you hear right when that diaphragm closes. That's the closing speed. So that's why it happens in such a half a second or so. So now you see the flow diminish, and then the red line shows that it's off. So in basically in this test, on this example, it went from starting to really move, the diaphragm really moving to close till it stopped the flow in basically 3-4 seconds kind of thing, right? But the part you would have heard, it would have been the last second or so. All right, so that's a big deal. And of course, the same thing would happen in reverse, and that's when you can see the rest of the on the graph here, that when they activate the solenoid, it launches open even faster than it closes, and that can be problematic too, and we'll talk about that. But so how do we control this surge that happens from a valve stopping the water? How much flow it's going through it, the valve. So we're going to size the valve correctly, not at the high end of its flow capabilities. The type of valve it is, not a pilot valve like in a valve and head, it goes very fast and there's almost nothing you can do. Where a solenoid valve, that gives us some leeway. And then the dynamic pressure that you're operating under, because this surge is going to be added to whatever the dynamic pressure is in the system, the working pressure, if you will. All right. So if you think about this surge, when you stop the water again, now we have the shock wave going back and forth, whether you're stopping the flow in the diaphragm valve, or if you're opening the manual valve, this ball valve, and especially these long levered, you see these 2 and 3 inch long levered ball valves, man, they're easy to operate, but they're death. It's so hard to get a technician to not slam these things open. Cracking them open, it seems to be not part of their vernacular. But at any rate, that shock wave just going slamming down when you open an isolation valve to fill that makes a big difference. Plus, it's going to, if there's air in that line, which especially after fixing a break or doing a valve maintenance or starting a new system up for the first time or after winterization, you get air in there and air compresses 7 to 10 times out of water. Now you've got, if you're charging the system at 80 PSI, 80 times 7 is over 500 PSI, right? 800 to 800 PSI of compressed air. Not very happy for a system that's not made to process that. And of course, the same thing would happen if this were all open and you slam shut the manual valve. Same difference. So again, the pressure wave that's created in here, often people call it a water hammer, is changing when the velocity change. And the bigger change, the bigger the pressure wave. Pretty logical, right? So the problem with most of this, other than compressed and trapped air, happens because it keeps happening over and over and over and over and over again. And 6, 8, 10 years into the system, depending on how egregious these surges can be, when you start to see some real failures. So long straight runs of pipe really can make a problem. So redway jobs are notorious. HOAs, big parks, things like that. You've got some real problems with long straight runs. We're talking about 3, 4, 5, 6, 10,000 feet of long straight runs become very problematic. All right, so if you're old enough in the irrigation industry, you may have seen this video. This is done, oh God, maybe in the late 80s, early 90s by Harco. And in the irrigation world, Harco ductile iron fittings, and Leanco ductile iron fittings are the two go-to fittings for this. But I want to show you what you have here is a ductile iron tee and a PVC tee. And you have water that's going to be set on a surge. It's plugged here and it's plugged on both ends of the PVC tee. And both of these tees are subjected to the same exact surge. And here is why we use ductile iron fittings for sure at 4-inch and up on directional changes versus non-directional changes, mostly T's and 90s versus PVC. So I'm going to start this. There's no audio, so don't worry about that. So I'm going to start. What I want you to do is you're going to see the PVC tee flex in a weird and wonderful way, and you won't see anything happen to the ductile iron fitting as you obviously would think. So here goes the surge, and you can see the surge comes and it pushes against that PVC tee, but it's also distorting the body of the tee immensely. You see it keeps repeating here. They're just cycling this surge back and forth, and that flexes. So you can see how that's moving at the fitting where the two tees are connected. There it finally gave way. The PVC tee split at the knit line. So that's just a pretty good visual representation of what's going on over time in your irrigation system in the ground. All right, how do these things manifest themselves? So there are a couple of these things they're called cyclical failures. One is called hoop stress, and like you saw in the tee, you actually saw the tee move back, but if you could have seen from the top, you'd see it actually bulging. If we had a better video quality, you probably see that, but you actually see it bulging as that shock wave went by. And that happens, and you can imagine as that travels, the shock wave goes down and it's flexing in PVC. That's all fine and dandy till you get to a joint, right? Big problem. The other one is inertia stress, and we kind of talked about that already, but that's the old object in motion wants to stay in motion, and the sharper the change in direction, the more disruptive it is. Plus, just that simple change in direction causes turbulence, which causes pressure loss, which causes a change in velocity between the inlet and the outlet, and that change in velocity actually causes another surge besides the force of just blasting against that T or that 90. So the other one is you kind of saw it on the PVC T, right where it was connected to the ductile iron T, but this happens and it's called pipe creep, and it's in the ground all along your main line. And it looks like this. So it's a shock wave, and as the shock wave keeps coming back, it actually causes the pipe to move in the trench, right? So there are things we can do if the pipe's going to move and it's super rigid, like solvent weld main lines can be. That can be problematic on all the joints. So we use gasketed fittings to help minimize that, a gasketed pipe. There's also the thing called dry line shock, which in time can be a real problem. And maybe you've actually experienced this if you've charged your systems in the springtime and somehow didn't control the flow of water into the empty pipe. And this happens on the lateral side. Everything we've been talking about before this really is happening on the pressurized mainline side. Dry line shock happens in an empty lateral, whether it's drained out from low head drainage or it's been blown out from the winterization or some maintenance or whatever's going on. And now you're just the normal sprinkler, the zone valve turns on and compresses the air. And then it comes, as the water comes down, it compresses, and that compressed air 7 to 10 times blows the sprinkler off the end or cracks the swing joint or any number of things along there. And if it keeps happening, it doesn't have to launch the sprinkler head into asynchronous orbit to cause a problem, although you obviously, at least it relieved the force, right? So there's another thing that adds to this damage besides the surge pressure, that pressure wave going through the water and the force of the water, the mass moving. The temperature of the pipe or the water makes a difference, because the temperature of the water would affect the temperature of the pipe. And so if you look at this example, if you look at the class 200 pipe, it's the same for all sizes. It's based on the standard dimensional ratio, the SDR, which has to do the wall thickness, excuse me, of the pipe and the inside diameter. It's that ratio. But it has a working pressure of 200 PSI at 73 degrees. And that's a typical deal. So if you did it at 80 PSI, you'll see the factor over there at 80 is you would diminish that pressure rating by 12%, or you'd have a factor of 0.88. So instead of 200 PSI at 80 degrees, it would be 176 PSI. At 90 degrees, obviously, let's see, at 200, it would be at 150 PSI. So, you know, some of us in the south of I-10 and out west, it's not uncommon to have 80-degree water being pumped out of the water source, and you know, a lake-fed source, and then have the ground be 80 plus. You agronomists knows you get ground temperature, soil temperature in the 80s, so it starts to add up. Doesn't have to be above ground though; it can be in the ground. Also, the expansive nature of the pipe. Now, obviously, as you would guess, PVC is the most flexible of all the pipe materials you see here. Obviously, we don't do too much carbon steel, CPVC, or stainless steel in irrigation systems, but we're using HDPE, and that's one of the benefits of HDPE is it's not very thermal. It isn't affected by temperature. But as the pipe gets warmer, PVC pipe gets warmer, it starts to expand per 100 feet. So that's inches per 100 feet. So if you look at an example here, if I had 500 feet of PVC and there was a 10 degree change, either rise, getting hotter means it's going to expand. If it's cold, getting colder, then it's going to contract. So 5 times 0.36, that's every 500 feet, it's moving almost 2 inches. That's going to be rather problematic in 1,000. That's almost 4 inches in a 1,000-foot run. So what do you think that might happen to a solvent weld joint, right? So as you can see in this graphic, if it's getting warmer, if that 10 degrees goes up, then you're going to expand the pipe against the fitting, and you're going to have warping and getting this angles of deflection in the fittings and or the pipe into their bell ends. And when it's cold, just the opposite, it starts to shrink. So again, the force that's involved on a 1-inch main line is not what is involved in a 4 and a 6-inch and an 8-inch main line. So it's the bigger the pipe, the more dramatic these exponentiate these effects. Gasketed, on the other hand, you're going to see the give at the gasketed pipe, the pipe fitting, and or the fitting into the opposite ends, and vice versa. So it's kind of like a shock absorber if you kind of expect effect. So entrapped air, let's talk about that for a second. Entrapped air is one of those things that can be extraordinarily explosive. You've actually been around one. I'm sure some of you might have actually seen a thrust block come out of the dirt with the force. It's a pretty amazing sight. But anyway, makes for a big hole. So let's talk about the sources of how the heck this air gets into the pipe to begin with. Obviously, and I put this one right at the top because this filling and refilling after repairs is a huge contributor to entrapped air that goes unnoticed by the maintenance crews. Because on the big systems, that entrapped air might take a while before it decides to congregate in a certain area. And I'll talk about that just in a second. And a lot of that comes from somebody value engineered the installation and said to the general contractor or somebody who only cared about the cost of the job, not the quality of the irrigation system. They said, you know, if your system has 28 isolation valves on the main line, you know, we really don't have to do that. We can do that with about 10 of them. Well, if you don't know what I'm talking about, what that causes is you have huge, long distances of pipe that have to be emptied for winterization or repair, drained down, and then have to be refilled. These long expanses, they're not short enough to be able to isolate the air and get it out before it goes somewhere else in the system. So you can isolate it much better, hence the name isolation valves. The pump turns on and off, turns off during like a power outage. It's running, system's running, and the power goes out, and the valves or the check valves don't work fast enough and or stick open. And now it causes, because the gravity starts to drain water out, displace it, and suck air in through the sprinklers while the valve or the check valves are open. The water source itself, you can have air come in. These changing in pressure, these surge pressures cause the dissolved air that's in the water to be released. So the temperature changes as well as the surge pressures will do it. And then of course, air relief valve or vacuum breaker that's in the system could be malfunctioning and bring it in that way too. So so how does this work? So once the air gets in, or it happens as a result of the things we just talked about, it accumulates in the high points of the system, right? And as this happens, as the air starts to compress and gather, it starts to compress more and more under pressure, right? And so it actually, the air starts to block the flow inside the pipe. And that makes the velocity trying to get by the compressed air get really fast. So now we have a surge, right? And so the water keeps flowing, and the compressed air is finally can be, maybe gets tight enough and forced, it can get pushed again down the line. So they can start with little pockets, they start to accumulate into big pockets further down the line. And so when it gets big enough, it pushes out towards the end of the sprinkler, and when it reaches the sprinkler, kablooey. Now this is a photo of winterization, but we've seen this happen as well, and it usually happens explosively, and that's sometimes when the main line entrapped air gets into the lateral line. It works just like the empty lateral line, like they drained it out, and it explodes sprinklers off the swing joints. So in the main line though, that velocity rapidly slows right there in the outlet, because now it lets it out, and it ends up being such a shock wave of the air finally being expelled and the water just stopping. Now it's like a valve closing. And Colorado State's done has a pretty kind of the landmark test in this entrapped air, 15 times operating pressure. So 100 psi times 15 is 1500 psi of explosive pressure where I come from. And you can see the result. This is a fractured the pipe and the T right there near where the sprinklers were connected. And obviously, if this surge keeps happening, the entrapped air keeps surfacing or keeps getting in and getting entrapped and then gets dislodged, it's going to wear and tear on the components, and pretty soon you've got a break regardless of how strong it is. All right, so there's sort of the anatomy. So let's build on this for the rest of the time and talk about what are the things we can do to incorporate some controlling measures in the different 4 stages of an irrigation system, from design to maintenance. So if you think about, excuse me just a minute. if you think about the piping system as the skeleton of the system, if you build a house with crappy framing, it really doesn't make any difference on the fit and finish, how well the plumbing is, how well the HVAC, how good the roof is. It really kind of doesn't make any difference after the fact, right? Similar with an irrigation system. If at the time of the initial installation or a new addition, if this isn't taken into account to control the surge pressures, there's just damn little you can do about it without huge expense. I have a client in Jacksonville, Florida, and they've got about 15,000 linear feet of roadway mainline on their common area, and 10,000 of it is 4-inch pipe. Unfortunately, it was glued. Wouldn't have been my suggestion, as opposed to gasketed pipe. And the compounding factor is the glue joints, the solvent welding joints were so poorly done. They're done by using a 1-inch dauber and not a roller or a mop to apply the cement, so they didn't put enough on. So if you do the math, every 20 feet on 10,000 feet, every joint is leaking. It's 22-year-old system. It's been leaking a long time, actually. And what's the cost to replace 10,000 feet under roadways, under sidewalks, through existing landscape? I don't even want to talk about it. So this whole thing could have been easily prevented. Easily prevented. Yeah, would it cost more money? You bet it would have. Well, not more than what they got to do now. So remember we talked about the velocity limit technique. At the design, the conventional thinking is 5 feet per second. You talk to most designers and you've probably seen it reflected in their designs. If you built a system by a designer who is worth their salt, you will often see it at the low 3s, 3.5, but under 4 feet per second, probably, in these long, straight, looped main lines with all sorts of things going on a big system. All sorts of things are going to happen. So think about this for just a second. If I design at 5 feet per second and the normal things transpire in every irrigation system, such as additional sprinklers, somebody adds some more sprinklers, somebody increases the nozzle sizes, or the one that you can't ever stop, if those first two things didn't ever happen, the seals around every single sprinkler will sooner or later start to leak. And by the time you catch them, it's not unusual for a gear drive rotor, to be leaking at 3 or 4 gallons a minute. In residential terms, that's as much or more than the flow of the nozzle. So now you've increased the flow in the pipe, and there wasn't a cushion for it. You're way over 5 feet per second. Now what do you have for surge damage? I mean, it was bad at 5 feet per second, but it's catastrophic above that. So let me show you this example. This is a PVC class 200 pipe chart. Now it's just a close-up of one, and I'll zoom in here just in a second. But if you had a 3-inch main line, and you were operating a number of zones totaling 20 rotors with 6 gallon a minute nozzles on a commercial application. So you got 120 gallons a minute. That's not uncommon. For the main line, if you follow conventional thinking, that'd be right at the top of, as you can see where it's circled, at 4.95 feet per second. So theoretical legal, you're under 5 feet per second. And somebody could say, well, we could make that 4-inch main line be 3-inch because we're still under 5 feet per second, and we can save you money. That's where the value engineering comes in, right? So you go down fat, dumb, and happy, and after, 7 or so years, the natural things happen that we just described, and now the 20 rotors are leaking an extra 3 gallons a minute apiece, and now you're up to 180 gallons a minute out of those 20 rotors that are running in multiple zones, and now you're at 7 and almost a half feet per second. Besides having a pretty good sized pressure loss, which compared to what it was, the surge pressures are exponentially larger as a result. at 7.5 feet per second versus 5. Let's look at 4-inch pipe. If they had designed it in 4 and they hadn't downsized it to 3, now brand new, it would be at 3 feet per second. So the designer did it at 3 feet per second. And let's say all those same exact things happened in 7 years from now. Now it goes up to 4.49 feet per second, under our 5 feet per second, probably makes a big difference. And we saved the velocity, reduced the velocity by 60%, the change. And that makes a difference between lasting 20, 30, 40 years or being really problematic after 7. And I work on these systems all the time, and it's very common in that 7 to 10 year window to have all the mainline T's and 90s, especially on a roadway job, start to create real problems and roadway failures. So anyway, so control the velocity, you control the surge pressure, right? So long straight lines, 4 feet per second would be way better. Not many designers do a large system at 5 feet per second at all. So that's one thing we can do with the piping. We can, during the design, we can make sure we're putting in gasketed pipes. So when those surges happen, we don't have the pressure on every single connection of every single stick of pipe in the ground, because it's got some give to that gasketed fitting, right? So it's pretty standard 4-inch and up. That's why it was so surprising on that job, even 20 years ago. That's 20 years ago, it was 4 inches and up was standard to not do solvent weld mainline on big, long straight lines, runs especially. So, but 3-inch and up is pretty common for most specifiers. Understand that the temperature makes a difference. So, thinking about what your water temperature is going to be, and what your soil temperature could be, and making sure you don't empty lateral lines by putting check valves on sprinklers. When you get to a big sprinkler, sports field sprinklers, you got a sports field that's pretty dang level. It's not a big problem. But on a park, a roadway, things like that around campus makes a big difference. Gasketed fittings as well. We saw the video, right? Pretty self-explanatory. Again, you'll see gasketed fittings used. I see 3-inch mainline that goes in solvent welded, and then they'll put a 2-inch repair coupling every 200 or 300 feet in the straight mainline run, so they can have the economies of 3-inch be solvent weld, but still have that cushioning every 200 feet or so. You go out west. If we got anybody from out west viewing this, that's a kind of a common thing on 2.5 and 3-inch mainline, is to have that repair coupling in there to give you that little shock absorber every 200 feet. Valves. We want to have valves that don't slam shut any faster than they have to. And the easiest way to do that is make sure we have a valve that is operating at the middle or at the low end of its flow range. So if this were an example of a pressure loss chart for a valve model number, and this one comes in a couple of different sizes, all the major brands have these. What you would do is you'd say, let's see what we got here. Look at the 1.5-inch valve, for example. It says that it can be used at the start of the pressure loss at 2.2. That happens at 20 gallons a minute. And where the highest pressure loss at 18.7 pounds is 125 gallons a minute. Now, nobody in my world would put 125 gallons through an 1.5-inch valve, regardless of whether the manufacturer said their chart said it was okay to do. That pressure loss would be too great, probably. But 2, anything at that 125 gallons a minute flow is going to slam shut. It's going to close very fast, faster than the average. The average, when you're at that 2 to 5 PSI loss range, that's when it's going to close in that 0.4 to 0.8 seconds. It's still going to close faster than a second, but we're looking for something If you're up at that 100 to 125, there's a good chance you're going in 1/10 of a second. So you want to stay at the high, the low end of the flow, middle end. You want to have at least 2 to 3 pounds of loss, but that's the ideal spot on valves. Okay? So again, the faster we stop that water, the bigger the surge pressure. I'm going to skip ahead there. There we go. Valves, manual valves. So we talked about the lever handle ball valves, which go for small diameter pipe for isolating out downstream from a valve or right at the valve, as that kind of deal. That's not a big deal. You can probably control that, but that's why we use this one right here on your right is a square operating nut gate valve. This happens to be a gasketed an O-ring gate valve, pretty typical in irrigation system for isolation valves. Manual angle valves, these are basically a gate valve that's on an angle. And then the Colonial valve in conjunction with Lasco, now called West something, they bought Lasco fittings. In conjunction, they have this slow closing ball valve. It's a regular ball valve. It's got the great features of the really good, strong, robust Viton. You can get them with Viton seals and that sort of thing, but it's geared so as you turn this knob, it's geared to close this very slowly, and it's way easier to avoid slamming a ball valve. So you get it's kind of the best of both worlds. Provide an adequate number of isolation valves. I told you that. That's a huge, as a maintenance guy for years, that's the pet peeve. Besides having to take all day to drain down a main line and all day to charge it back up, for people that really are conscientious not to have it filled too fast. It's the people that aren't conscientious that the not having the isolation valves is going to be death to that system really early. Other things in design: continuous acting vacuum relief valves, variable frequency drive pumps, pressure relief valves at the source, air chambers or surge tanks, maybe even if it's unavoidable. All kinds of things can be designed into the system to try to get that surge controlled. During the installation, I know this is going to sound funny, just how the pipe is handled and stored. Dragging, dropping, that sort of stuff, throwing stuff off trucks, driving the truck down through the field and throwing the pipe off and to stage it, to put it in, big problem. We already talked about solvent weld for small diameter pipe and how to do it and make sure you do it well with the right size applicator, big deal. The value engineering, again, downsizing the pipe, eliminating the isolation valves, reducing the zones valve sizes, all those things are bad. Using gasketed, instead of using gasketed, using solvent weld, and again, reducing the number of joint restraints or thrust blocks, big problems. And again, once those are in, it's a do-over to fix it. There's no easy fix. Now let's talk about management, because I'm sure there are many of us on the call now that aren't really installing, but you're fixing and managing the system, right? So let's talk about making sure that you might have the high flow zones. Let's ramp down these high flow zones to lower flow zones before we go to no flow in the main line. Sequence those valves differently so the lowest flow you can possibly get lasts right before you turn the pump down. Now, retrofitting with variable frequency drives is a pretty common thing now and much more economical in the last 20 years. So you can take a fairly small, even a 5 or 7 horsepower pump station or booster pump, have a variable frequency drive put on it for under $1,000, which would get you a real ahead of the game in this regard. Making sure how you schedule multiple zones simultaneously, how you start and stop them, things like that. Maintenance, making sure that you're really cognizant of refilling the pipe with water when you start it up in the spring or your repairs, right? I don't know how to determine what 1 foot per second is, but it's pretty dang slow. Think about it. If the system's been designed for 4 or 5 feet per second, this is between 4 and 5 times slower than normal flow. So pretty big deal. You may have to cut in some more isolation valves to make this more feasible to do this on your system. Make sure those air and vacuum relief valves are maintained pretty regularly. Understand the hydraulic effects of what happens when you add a sprinkler, what you do when you increase the nozzles. If you don't monitor pretty frequently in that starting about year 3, 4, 5, depending on the quality of water and the abrasiveness of the soil the sprinklers are operating in, you may want to start looking at those leaking seals. But as that flow goes up, so does the velocity, because your pipe size isn't changing. Okay. So you guys haven't been asking any questions, so I'll kind of wrap up here. I think we're doing pretty good on time. Let's see here. Oh yeah, great shape. All right, so surge pressure, all we can do is try to minimize the damage. We can just try to control it and minimize it, right? This is way, way more than just a design issue. We've seen really crummy maintenance and management, or worse, installation. You could have a great design, a great installation, and maintenance management really hammer it, pun intended, due to pressure surges. So here's the hard part. At the time of installation, it's one thing to do the cost benefit analysis, but that's the time to for sure do it. You can't allow somebody who is more interested in coming in under cost be in charge of doing the cost benefit analysis on this, unfortunately. But those undershift costs will go through the roof if you don't understand the value of putting some of these things into the system. After the fact it's in, there's some things we talked about you can do, but again, there's still maybe some cost benefit to doing some of that stuff, like cutting in more isolation valves and things like that. So let me leave you with a couple of other additional resources. I'll give you my phone number and my email. And if you think of something, or you were just too shy to ask while we were doing this presentation, or you're watching this in recorded version, feel free to email me and we can have a discussion, either email, text, or over the phone, and clear up any of those questions. But some additional resources for you. One is sorry for the blatant plug. You can go, that QR code, you can do that, and that'll take you right to our course catalog, and you can see the nearly 200 hours of training we have on irrigation and irrigation business. The 6th edition by the Irrigation Association is probably, well, it's industry standard, and I hold this up just because I want you to know it's if you don't use it very often, it really will hold the door open. And for the springtime breeze, it's really kind of nice for that summer breeze. No, this is the resource to go to. And I will tell you that when I do those justifications, I do those analyses, people always go, Kurt, is that really your opinion, or can you back this by fact? Well, you want to know how the sausage is made scientifically. Here it is. And quite frankly, chapter 7 in hydraulics in that book covers, there's the section on surge. It's probably the best written surge. There's a bunch of really crazy formulas in there, but you don't have to really make friends with those conceptually, but really well written. And then this Designing, Operating, Maintaining PVC Systems booklet is actually a research study that the Irrigation Association did back in the late 80s, and it's out of print. But I have copies. Still have it in PDF, and it's not copywritten, so I can share it with you. But if you would like that, and because you want to know about working with PVC from solvent welding to the surges we talked about, it's sort of the benchmark study in the irrigation industry. I'd be happy to share that with you. And I think, Kristen, I guess there are no other questions to field, since you didn't bring them up.
No, if anybody has any questions, go ahead and type those into that Q&A feature. And Kurt, do you have a slide with your contact info? There it is.
There we go. So down at the bottom in the yellow, that you can, there's my email and my phone. You can text me, or you can call me, or whatever. It's probably better if you text and arrange a time for us to have a conversation, or email me, because I probably don't have your phone number. And you'll have to leave a message, because I'm pretty good about not answering phone numbers I don't know this day and age. So at any rate, thank you very much for your kind attention, and we look forward to being involved with more of the association irrigation presentations we can support you guys with.
Great, thank you, Kurt. And again, if you guys need to get in touch with him, there's his contact information. So thank you, Kurt. Thank you all for joining us today. Have a great rest of the week.
Bye all.